Welcome to the video for 4.4, a closer look at ionisation energies. If you need to look at your textbook, then it's pages 80 to 81. A lot of the material covered in this video is just revision really of what you did in section 1.6 when we looked at ionisation energies. So some of the slides overlap with that. So apologies for that. However, if you look at the chapter in the textbook, it doesn't really contain any new information. So we're going to go through this fairly quickly. If you need a more detailed explanation, then go back and look at the video for 1.6. So our lesson objectives are to describe and explain the trend in the first ionisation energy of the element sodium to argon. And a little bit of revision first of all, there are key definitions. So first ionisation energy is the enthalpy change when an electron is removed to form a unipositive ion from a gaseous atom. And the second ionisation energy is the enthalpy change when an electron is removed to form a dipositive ion from a gaseous unipositive ion. Again, this is a slide from the previous video, so go back and look at that if you want it in more detail. So a quick recap, and this is just a slide stolen from the previous video. Quick revision about the factors that affect the ionisation energy. So there's three factors that affect it. First of all, the nuclear charge, so how many protons you've got in there, so how much positive charge there is. Secondly, the distance of the electron from the positive nucleus. And thirdly, the amount of shielding between the positive nucleus and the outer electron. So here's a graph showing the general trend going across. So you can see as you go across the period from sodium to chlorine, there's a general increase. So you can see a general increase going across the period. However, there are two places where it goes down, and that's what you need to do about in more detail. So first of all, we'll talk about the general case. So in general, going across a period, the nuclear charge increases, which would tend to give you a higher ionisation energy because there's more attraction between the positive charge and the electron. The distance of the electron from the positive nucleus decreases, so again, because the outer electron is closer, there's going to be more attraction between the electron and the positive nuclear charge. So because you've got a greater attraction, you're going to need more energy to overcome that. So that's also going to tend to give you a higher ionisation energy. The third factor is that the amount of shielding between the positive nucleus and the outer electron stays the same. So because the electrons are going into the same shell, there's no more shielding there was, so that stays the same. So you've got three factors, one stays the same and two tend to give you a higher ionisation energy. So it's no surprise then that what happens is you end up with a higher ionisation energy as you go across the period. So that's why you get the general trend. So if you look back at this slide that I showed you before, you can see that general trend of going up. So from sodium to magnesium it goes up, from aluminium to silicon and phosphorus it goes up, and from sulfur to chlorine it goes up. And that's because of the factors we've just discussed. But you can also see you've got a dip from magnesium to aluminium and from phosphorus to sulfur. So we need to look about why this happens. And the reason why that happens, there's two separate reasons. So between groups 2 and 3, so this is general for the periodic table, but between groups 2 and 3, the first ionisation energy will go down rather than go up as we would expect. And in this case, it's between magnesium and aluminium. And this is because in groups 1 and 2 are in the S block, so their outer electron is in the S shell. However, once you go to group 3, you're talking about the P block. So the outer electron is now in the P orbital. So in the case of magnesium and aluminium, you're going from a free S orbital to a free P orbital. And as you know, the free P orbital is slightly higher energy than the free S orbital. So it's slightly further away from the nuclear charge, and therefore the attraction is going to be less, and you're going to have more shielding. So it's going to be slightly easier to remove that outer electron. So the elements in group 3 will have a slightly lower ionisation energy than the equivalent one in group 2. The second place where it goes down is between groups 5 and 6. So for period 3, this is phosphorus to sulfur, and this also goes down, but for a different reason. Now in this case, when you're in group 5, you've got one electron which is unpaired in each of the orbitals. So for phosphorus, you've got 3p3. So you've got 3p orbitals, and each one of them has got one electron in it. When you go to sulfur, you're adding a fourth electron, and because there's only 3p orbitals, that fourth electron has to go into an orbital which is already occupied, which means you're going to get some electron-electron repulsion because you've got two negative species in the same space. They're going to repel each other, and that repulsion makes it slightly easier to remove that electron, that outer electron, which means the ionization energy is slightly lower than you would expect. So the last thing we need to talk about is successive ionization energies, which again we've covered before, so it's just a bit of a recap. So each electron that's removed is going to take more energy because you are removing that electron then from a positive species. So it's more difficult to remove an electron from a species that's already positive than it is if it's a neutral atom. However, we can use the successive ionization energies to work out which group an element is in. So if you have a graph of the successive ionization energies, or if you've got a chart giving you the figures, then you can work out which group it's in. And the reason you can work this out is because the electrons in the outer shell are going to be easier to remove because they're further away from the positive nucleus and they have more shielding. So therefore, when we see a large jump in ionization energy, that's when a new shell is going to have been entered. So we can look at this slide, which is from the previous video, so you should have already seen it. I'm not going to talk in detail here because I talked in the last video about it. But basically, the red boxes show where there's a big jump in energy, and where there's a big jump in energy, that's where you're entering a new shell that's closer to the nucleus. So you can see from those energies, there's a big jump between the second and third electron for magnesium, so therefore it's in group 2, because the first two electrons come from the outer shell, and then the third one is coming from the next shell down. The silicon is in group 4, which you can see because there's a big jump between the fourth and the fifth ionization energy. And lastly, aluminium, there's a big jump between the third and the fourth, which tells us that it's in group 3. So here's a recap of our lesson objectives, which were to describe and explain the trend in first ionization energy of the elements sodium to argon. So as usual, if you don't understand this lesson objective, then go back and watch the video or look at the textbook or look at some online notes in order to understand it before you come to lesson.